All right, we are back. So during this recording, I want to begin the classification of when continuous functions exist. And the end goal is, as stated right here, that, well, okay, so that's not a statement, that's not a full sentence, that if you have a uniformly continuous function, then it will have a continuous extension to some set. And let's start by specifying what that set is. So you'll notice that evaluation of limits at limit points was relevant. So that's exactly where we'll try to extend them. So the two previous examples of functions, which did not have continuous functions, failed to have a continuous extension because there was a limit point in the domain where the limit of the function was not defined. Right? That's basically how the proof went. So here's what our goal is. We will prove that if a function f is continuous, and the limit as x approaches p of f of x is defined at every limit point of its domain U, then that continuous function extends to a continuous function over all the limit points of U. And if that's our goal, let's make up a definition. So here we want apparently to extend f over the set of limit points of U. So let's just describe that set. Definition 3.9.7. For any subset U of R, the closure of U is given by U with a line on top of it. Sometimes you'll see this written as closure of U, but I'm following, if you like, the book notation where I'm using an over line. Since there's not any complex conjugation in this class, I don't think there will be any confusion there. I think that's not true. Well, maybe. Yeah, I bet it is. In a benchmark, at this point, you will have proven that the closure of any set is closed, meaning U bar contains all of the limit points of U bar. So here's a reformulation of the closure. For any set U, the closure of U is given by... that comma doesn't need to be there. The closure of U is given by the union of U with all of its limit points. That is, U bar is equal to U union the set of all x such that x is a limit point of U. And let's just, off to the side, remember the definition. X is a limit point of U means for all delta greater than 0, there exists some element, doesn't matter what you call it, y in U, such that 0 is less than absolute value, x minus y is less than delta. And maybe that's not the definition you were expecting me to write. Maybe you wanted me to write the one where instead of U here I have U different from singleton x, and where that isn't there. But notice that gives the same thing, right? This 0 is less than has the purpose of saying that y is not equal to U. This has the purpose of saying that y is not equal to U. So, same definition. So, U bar is the set U together with all of the limit points of U. How do you show two sets are equal? Well, we just need to prove two reasonably straightforward set containments. Let's do that. So, let's prove the forward containment. Consider any x in U bar. If x happens to be in U, then we are done. Why are we done? Well, let's see. If x is in U, then as U is contained in U, unioned with any set, in particular, the set of all x such that x is a limit point of U, x is in U, union with the set of all x such that x is a limit point of U as desired. All right, we'll consider any x in U bar. If we can get x to be in this set, then we're done. So we may as well assume that x is not in U. We now need to show that x is a limit point of U. So here's what we'll do. We'll consider any delta bigger than 0. We need to show there exists some element. It was y off to the side, but it doesn't matter what you call it. There exists some element, little u, in a set big U, which satisfies that 0 is less than the absolute value of x minus u is less than delta. Well, let's use the fact that x is in the closure. We haven't done that yet. Since x is in the closure, then this has to hold true. And we've already considered any delta, so I don't need to redeclare delta. So I know that something happens for every choice of delta that's positive. I have a choice of delta that's positive. So let's see, since x is in U bar, by assumption, we get that there exists some little u in big U such that absolute value of x minus u is less than delta. This is by the definition of x of u bar. Oh, so neat. That gives me most of what I need. I need to show, so what do I have? I have there exists a u in u such that the absolute value of x minus u is less than delta. I wanted to show there exists some u in u with 0 is less than the absolute value of x minus u is less than delta. I'm just off by this. That's all I need. Well, let's try to get that to show up. So remember what the purpose of that 0 is less than is. That purpose of that 0 is less than is just to say that x is not equal to u. Why is x not equal to u? Well, we need some property that x has that u does not. X is not in u. U is in u. Aha, I think that does it. As x is not in u, and little u is in u, x is not equal to u, so absolute value of x minus u is greater than 0. And now let's just summarize. Thus, for all delta greater than 0, we have found a u in big U such that 0 is less than the absolute value of x minus u is less than delta. Thus, x is a limit point of u, and so okay, I guess I can just carry on. Thus we see that x is a limit point of u, and so we can conclude that u bar is contained in u together with the set of all x's such that x is a limit point of u. Well done. Now let's do the other containment. That felt pretty easy, I hope. Not too abstract. It should have, that was a reasonably straightforward argument. So let's go the other way. Let's consider any x in the other set, any x in u together with the set of all limit points of u. Well, there are two cases then. If x is in the union of two sets, either x is in u, or x is in the set of all x is such that x is a limit point of u. Well, there are two cases then. Either this is true or that is true. Whenever you see that situation, maybe a case-wise argument is in order. Let's try to complete the proof when x is in u. In order to show that x is in u bar, we have to show that for all delta greater than 0, there exists some little u in big U such that the absolute value of x minus u is less than delta. So there's what I need to prove. So let's consider any delta bigger than 0, and I need to come up with a choice of little u. Maybe I'll go off to the side and draw a picture of the current situation and see that there's an obvious choice. So let's do that. So there's just a number line. There's the set u. I know right now that x is actually in u. Well, given the fact that x is in u, can I find something in u that's really, really, really close to x? How about I just use x? Will that do the trick? Let's just do it in our heads before we do that. So let's take x to be u. Is x in u? Yeah, it is, by assumption. Is the absolute value of x minus x less than delta? Well, yeah, it's equal to 0. 0 is less than delta because delta is bigger than 0 by assumption. So that'll do. Consider any delta bigger than 0. We'll let x be equal to u. Then, well, let's see. As x is in u by assumption, u is in u, and no, let's try to be grammatically correct. Full stop. Moreover, absolute value of x minus u is equal to the absolute value of x minus x is equal to 0 is less than delta, since delta is greater than 0. Thus, by the very definition of u bar, x is in u bar. Because what have we shown? We have shown that for every choice of delta, there exists some u, which is in big U, and which satisfies that the absolute value of x minus u is less than delta. But that was only half of this piece of the proof. Now let's suppose that x is in... we're done in this case. Now we need to walk in that case. Let's suppose that x is a limit point of u bar. In that case, well, let's see what we see. Since x is a limit point of u bar, we know that for every delta greater than 0, there exists some u in u such that 0 is less than absolute value of x minus u is less than delta. Oh wait, I think that means we're just done, right? I just don't care about that. I know that, but I don't care about it. So let's see, since 0 is less than the absolute value of x minus u is less than delta, we have absolute value of x minus u is less than delta. Since we have this, thus, for all delta greater than 0, there exists some little u in big U, such that absolute value of x minus u is less than delta. And notice that's exactly what it means to be in u bar. Thus, u is in u bar. Nope, x is in u bar. And so, that completes the proof of set equality. Nice. So, here is the main result that we will prove. Suppose that f from u to r is a continuous function, which satisfies that at every limit point p of u, the limit as x approaches p of f of x exists. Then there exists a continuous function g from the closure of u to r extending f. So notice, what does this say? This says if we happen to have a function that always has limits, that you can take limits of at every limit point, then you can extend that continuous function to a bigger domain which contains all of the limit points. That was our goal. Oh, neato. So, what type of function do we have which satisfies the limit as x approaches p of that function always exists? Well, uniformly continuous functions, of course. So let's suppose that f from u to r is uniformly continuous. Then there exists a continuous function of that uniformly continuous function. And you know what? I think this is a good place to break again. We'll come back with probably the remainder of this packet. Great, talk to you soon.